Right, so hi everyone, another installment of the department seminar. I'm very pleased to be joined today by Debashis Mondal, and he's going to be talking about some things that I believe about spatial statistics, and hopefully his slides will work. So over to you.
Thank you, Nathan. Thank you for the invitation. I'm going to share my screen and hoping everything will work great. Feel free to interrupt me if you have any questions. I can't see all of you, so you may just speak up. Okay. So this is a joint work with my former PhD student, Somak Dutta. He is now an associate professor at Iowa State University. There is a part in his PhD thesis that has some of these ideas, and that it goes back almost several years ago now, almost like 2015. But it took us some time to kind of shape some of the ideas, and we are almost ready to submit a paper on this. Here is an outline of the talk. I'll try to explain the problem here, kind of give an overview of the prediction problem in spatial statistics, and I'll describe or discuss some of the computational challenges. And then we'll talk about this new algorithm on conditional simulations and for predictions. This algorithm will work for regular as well as irregular lattices, and they cover a large class of spatial models, not just Gaussian Markov random fits. And we are going to come to some of those details. I'll show you a couple of applications from environmental sciences. So here we have some data on groundwater arsenic contamination in Bangladesh. Each of these dot here is a data point, and then the values are here. We are plotting it on the log scale. This data was collected by British Geological Survey, and it's available online. What we can notice is that there is a large area somewhere in the middle where contamination is very high, and even though we have about 3,000 locations at which the data is available, there is interest in terms of how the arsenic contamination is across the entire country. Now it's a serious problem. About 42 districts is above the World Health Organization's maximum permissible limit, which is 50 mg per liter. And in Bangladesh, many millions of people are affected due to the arsenic contamination. And many papers are written on this topic in Nature and Science. Our goal is to look into this data and analyze this data from a spatial statistics point of view. What I am showing you here are base linear unbiased predictor, or like our creaked estimate of arsenic contamination. So there are three pictures here. These are for three different spatial models. How we do this exercise is as follows. We kind of maybe embed the data in a very fine grid. Here 500 cross 300 grid points, and then we have a Gaussian linear mixed models, and we fit the model, and then we predict the arsenic at any of these grid points across the country. Now, as I said, there are three different models, or maybe it's this one model, and there are like three different parameter values. So the leftmost one corresponds to Gaussian Markov random fields models. So here the inverse covariance matrix is a sparse matrix. The middle one corresponds to a fractional parameters. Based on fractional Gaussian fields, and so in this case, the inverse covariance matrix is actually a dense matrix, but it does not have any nugget effect. And the right one corresponds to, again, another fractional Gaussian fields. This one has, again, a different fractional parameter, but this one also has a nugget effect. And the rightmost one is actually based on the Reymol estimates. Now, these kind of Kriging or base linear unbiased predictor, these are often the starting points because we also care about uncertainties. So it's not just about computing the conditional mean, but we want to do more. And what do we mean by we want to do more? Many inferential questions would require us to look into the joint distributions of various unknown quantities and kind of computing high dimensional probabilities. So here is one example where we are interested in, say, predicting aggregate arsenic concentration exceeding the WHO limit, the World Health Organization's kind of cutoff, 50 mg per liter. Condition on the data. And when we are saying that we are interested in aggregate arsenic contamination, so what we have here in this map is kind of different sub districts. So these boundaries and those small areas, they each of them correspond to a sub district in Bangladesh, and we are interested in asking this question within a sub district. If we look into the aggregate arsenic concentration, what's the probability that it will exceed this limit? And for some regions, this probability is very high. So the way this was computed is as follows: we kind of put everything again in a very fine grid, and then we did many realizations or simulations of the conditional distributions or the predicted distributions. And then we kind of, every time, we have a simulations, we can compute these aggregate arsenic concentrations within a sub-district, and we can check whether it is exceeding the limit or not. And then this computation is done by taking Monte Carlo averages over 20,000 rows. So here are some other probability calculations. On the left here, what I'm showing you is the probability that maximum predicted arsenic concentration within a sub-district will exceed the cutoff limit. And because it's maximum within a sub-district, now many more areas are showing up with high probability as opposed to the average or the aggregate concentration. And then on the right, what I'm showing you is actually so to explain this one, there is interest in maximal exceedance region. We may think about a sub-region within Bangladesh where everywhere the arsenic concentration is above the cutoff limit. Now, then we would be interested in, for any particular kind of small area or cell within Bangladesh, and we can ask this question: what's the probability that this particular small area belongs to that exceedance region? And so what we can do, we can compute the average exclusion probability of each cells in this maximal exceedance region. And we see that some of the cells, they have very high probability of being part of this maximal exceedance region. On the other hand, there are other where the probability is low. So we can get informations about the maximal exceedance region in this way. Then there is interest in contour plots various kinds of contour plots. So here, for example, the green line is showing us the contour plot where with the who recommended cutoff limits, whereas the blue lines are for I mean, it's still somewhat significant arsenic contaminations, but maybe not as harmful as but it's about like 10 ml mg per liter. For a slightly different cutoff. So these kind of computations would typically require conditional simulations, or simulating the concentration of arsenic at all possible locations given the data. And it's a challenging problem. So the one of the questions we'll address is how to do these conditional simulations, what kind of algorithms we use currently, and can we improve or do something better. Now, for predictions with, so we are going to focus on spatial linear mixed models, and so for these models, our observations Y would be a Gaussian response, and so we are thinking about the simplest possible model here. So we have Gaussian response, and kind of we are focusing on the identity link functions, or just the modeling the mean part. And so the model will be written in kind of in about 3 terms. One term will involve maybe we have some covariance effects, and we have some design matrix or covariance information matrix. Then we have a random effects component here, and primarily this is our spatial effects. And so we also have a particular kind of multi-purpose linear matrix F. It could, in many applications, these are incidence matrices, but in some other applications, these can have maybe different interpretations, like it's an averaging matrix or some other kind of sparse matrix. And then we have the residual error or the nugget effects epsilon. And typical assumptions might be that maybe we have a fixed effect tau, and then these random spatial effects and nugget effects, and we use this kind of model to do predictions and to do conditional simulations, or in other words, we use this kind of model to do statistical inference. And we also need some stochastic modeling for this spatial random effects X. Now, so for spatial random effects, here we can think about some of the simplest model. And so I studied spatial models with Julian Bissag, and he introduced these conditional and intrinsic autoregressions for spatial random fields. So here the idea is that maybe observations are on grid points, and then we have this variable XUV in the middle, and we want a model for all these spatial variables. So we can think in terms of conditional distribution. We can ask what's the conditional distributions of this XUV given all other X values on all other grid points. And we can say that this conditional distribution is again Gaussian. The mean is kind of weighted average of the near about values, and the variance is constant. And it turns out that this gives rise to one of the simplest models for spatial models, known as conditional autoregressions. In some sense, these are generalizations of autoregressive models in one dimensions, or maybe we can also say random walks models in one dimensions. And so these kind of models, they would behave like a stationary Gaussian random fields if the value of these two is less than alpha, but at the boundary these are known as intrinsic models because they have in this boundary case the inverse covariances, they become a singular matrix, and we do not have covariances, but we have everything defined in terms of variograms or differences of the observations. Now, these kind of models are particularly interesting in the following sense, like in one dimensions, where we know that AR1 time series, there is a continuous limit, so it converges to the Ornstein-Uhlenbeck process, or we have random walks in one dimensions, and if we kind of look into fine and fine lattices, then the random walk converge to the Brownian motion. Similar thing happens in two dimensions. If we look into finer and finer lattices, then these stationary and intrinsic autoregressions, they have some geostatistical limit process. So those intrinsic autoregressions in the limit, they converge to an object that is known as the Debashis process. It's also known as the Gaussian free fields in the probability or quantum physics literature. And then the stationary version, they also converge to a process known as the generalized Ornstein-Uhlenbeck process. So unlike in one dimensions, these limit objects are a bit more complicated. For example, the Debashis process, is not defined pointwise. So on any particular point in the two-dimensional plane, if we think about the limit object, for any particular point, these would not correspond to any random variables. However, if we look into some aggregates or averages over a small or any area, then those aggregates or averages, they would start to behave like random variables. And in the case of Debashis process, when we look into contrast between averages, they have Gaussian distributions with a specific mean and a finite variance. So then they become well behaved. But still, the idea is that if we have a very fine grid, we can use the functionals of these conditionals or intrinsic autoregressions on the lattice to approximate the appropriate functionals of this continuum limit process. So the whole idea is that even though we have these geostatistical limits, they are a bit complicated. We can still use our lattice processes to approximate appropriate functionals of the geostatistical limit. So here, what I am showing you is a realizations of intrinsic autoregression on 256 by 256 array, and you can see some patchiness and you can see that the values are a bit kind of dependent or correlated. So that's how some of the basic spatial process Gaussian processes look like. Now we are interested in statistical estimation and inference. So we will focus on this kind of mixed linear models, and we need to talk a little bit about the residuals and some of the other terms, and then ask ourselves how we generally proceed to do statistical inference. So for that, here we have some of the simplest assumptions. So let's assume that the residuals, these are IID, a normal mean zero, and it has an variance parameter or precision parameter. This might be a fixed effect, but let's also assume that this is a random effect, and it's also mean zero, and it, kind of every component is, IID, and it also has a variance parameter or a precision parameter. And then what happens is, we have this spatial effect coming from a conditional or intrinsic autoregression. So it has its own inverse covariance matrix, and this inverse covariance matrix here is denoted by W. So it turns out that if we do these calculations on a regular grid, then this inverse covariance matrix or the precision matrix of the spatial random fields, it has a spectral decomposition, and that is known analytically. In particular, so we have these spectral decompositions where all the eigenvalues would correspond to two-dimensional discrete cosine transformations, and all the eigenvectors correspond to two-dimensional discrete cosine transformations, and the eigenvalues they are again known analytically. Now, in the frequentist literature, all these precision parameters they will be fixed but unknown. But in the Bayesian context, one may think that maybe we want to put some kind of prior on them. And so and then we proceed. So in the Bayesian context, we try to compute the posterior distributions and then do predictions. On the other hand, in the frequentist context, we have to estimate these unknown dispersion parameters, and then again we have to for predictions we have to look into conditional distributions. Here, because we are assuming that tau and x both are random effects, and so if we need to think about inference, then the first thing would be what's the distributions of these random effects, condition on the data and the parameter values. And as I said, in the classical case, we have to estimate these parameters to proceed to inference. It turns out that these random effects, will, because these are Gaussian random effects, and we are looking into Gaussian, linear mixed models. So this conditional distribution will be a Gaussian distribution, and its mean and variance have a very specific form. So the mean is represented as A inverse B for some matrix A, and the variance is A inverse. And so what is this inverse covariance matrix A? This inverse covariance matrix A has this specific form, and then B is just a vector. Now this matrix A has some particular structure. This W is the inverse covariance matrix of the spatial random fields, and then this F transpose Fs, it comes from that incidence matrix, and this is again a sparse matrix. So this block here is actually a very large matrix, and but it's a sparse matrix. On the other hand, we have contributions that comes from the other random effects, and these are kind of smaller dimensional matrices. In some applications, they can also be large dimensions, like there might be some high dimensional random effects, but in that case, generally those design matrices will also be kind of sparse. So what happens is when we look into these conditional distributions, even though it has this specific form, the mean is A inverse B and variance is A inverse, typically the matrix A is a large sparse matrix, and we need to simulate Gaussian vectors from these distributions in order to do statistical inference, and because some of the inference requires computing high dimensional integrals. Now, the current state of the ART algorithm, and this is due to work of Hobart Roux and Leonard Held, it focuses on sparse Cholesky decompositions. And so if we have a very large matrix A, the idea is to look into the sparse Cholesky decompositions of this matrix. And once we compute the sparse Cholesky decompositions, then we can actually simulate from these Gaussian distributions. However, the tricky part here is that sparse Cholesky decomposition is actually not a scalable computation. And so typically the order of computations for R cross C grid will be about R times C to the power 3/2. And this is on kind of planar grid. If we are thinking about, say, three-dimensional grid or some kind of space-time problem, then this power it gets worse. It becomes more like number of grid points square rather than 3/2. And that's what it means is that this this sparse Cholesky decomposition does not lead to a scalable computation. The other thing is, even though this matrix A is sparse, this sparse Cholesky AL doesn't have to be that sparse. So typically there are fill-ins that occurs during the sparse Cholesky computations, and so the matrix AL is typically less sparse than matrix A. And what it also means that you have additional memory requirements, so you need more in order to store this matrix L. And these are kind of concerns, particularly for large matrix calculations. And even though we are talking about kind of sparse matrices, these kind of computations can fail beyond a point. And one of the question is, how should we then do statistical computations? If there is any way we can actually do more scalable computations with fewer kind of with kind of minimal memory requirement. It turns out that if we only think about the base linear unbiased predictions or the Kriging computations, there is an alternative solution. And so I'm going to talk a little bit about this alternative solution, particularly for the Kriging problem or the base linear unbiased prediction computation. It turns out that these computations can be done in a scalable way, where we have fewer memory requirements. And what we are doing here, we need to compute this A inverse times B, which is a particular vector. And this will give us the base linear unbiased estimator of these fixed effects, as well as the base linear unbiased predictor of the spatial effects. And here, the whole idea revolves around kind of solving a sparse linear equation rather than looking into sparse Cholesky decomposition. So the whole idea is that we want to solve maybe A beta times B, where A is a sparse matrix. And it turns out that this can be done very efficiently with what we call the Lang-Jost algorithm, or maybe a Krylov subspace algorithm, or in some other cases, the literature will talk in terms of conjugate gradient methods. And so the idea is that we can sequentially compute orthonormal vectors v1, v2, etc. From a kind of span of these B, A, B, A square, B, etc. Those are the forms the Krylov subspaces. And then kind of reduce this matrix into a tridiagonal form. And once we have this tridiagonal form, then when we try to solve it, essentially it becomes solving a tridiagonal system of equations, and for which the computation is very fast. Here, we really do not need to store any of these matrices because these computations are done sequentially till it converges. And so one can also show that the effective order of computation is just like, for R cross C grids is RC times log RC. So for n grid points is essentially n log n. And that's why these are scalable. And also it does not require storing any matrices. And this algorithm can be improved even further by using what we call preconditioning matrices. And the idea is not to solve a beta equal to b directly, but to introduce another matrix C, some kind of convenience sparse matrix C, and kind of solve CA C transpose B equal to CB, and then C transpose B equal to beta. And here the idea is, we want to choose a matrix C, which essentially is not a Cholesky decomposition or kind of, like inverse square root, but is something similar. And this is where, what one can do. There is a concept of incomplete Cholesky decomposition. It's not an exact Cholesky decomposition, but this incomplete Cholesky decomposition is very fast. It requires minimal storage, and it is a scalable computations. So for like n cross n matrix, sparse matrix A, this would require like order of n storage and order of n computations, and this can be used to find a very nice preconditioner and then kind of solve this linear system of equations, and the convergences are great. And so this is what actually improves upon the sparse Cholesky decomposition. And then the question is, can we not do something similar for conditional simulations? Because we can do better for the Kriging problem. So naturally the question is, what happens to the conditional simulation problem? It turns out that there is a kind of solution here, and it's kind of interesting in the following sense. So this solution cannot avoid any matrix factorization. So we need to have some idea of kind of matrix factorization, but then we can combine it with this kind of matrix solving equation. And so here is the idea how we can improve on computations and then still do kind of fast conditional simulation. So again, the objective is to simulate Gaussian vector from with mean A inverse B, and variance is A inverse. So A is that large inverse covariance matrix. It turns out that even though A does not have a kind of a very nice sparse Cholesky decomposition, what it has some kind of rectangular decomposition. And so this is where we are going kind of beyond the traditional matrix factorization. And one can write this matrix A as some S times S transpose, where this matrix A is no longer a square matrix, but rather it's a rectangular matrix. And this is, there are different ways to kind of do this in, rectangular decomposition. One way to do this rectangular decomposition is to use these eigenvectors and eigenvalues of that spatial block A. So this matrix M here corresponds to the two-dimensional discrete cosine transformations, and then the D is coming as our eigenvalues of our spatial inverse covariance matrix. And once we have this kind of rectangular decompositions, then the whole idea changes, because we can kind of generate IID Gaussian vectors, and then maybe we can multiply those Gaussian vectors with this matrix S, and this will actually generate as Gaussian vectors whose mean is 0 and whose variance covariance matrix is A. So this time, in the first step, what we are doing, we are simulating Gaussian vector with mean 0 and with a sparse covariance matrix rather than sparse inverse covariance matrix. But once we do these simulations, then what we can do, we can go back and kind of do our Kriging problem or solve a system of linear equations. So this time we will solve A times beta equal to B plus U, and then this will give us the beta will then become, so in this case beta will become A inverse B plus U, and then this is our Gaussian vector, and so this will give us realizations from normal distributions with mean A inverse B, and the variance would be A inverse variance of U, which is A, and then A inverse, and the whole thing will become A inverse. And that's how we can kind of proceed to computation. So what we need here, we need this kind of rectangular decompositions, and then which would enable us to simulate Gaussian vectors with a sparse variance covariance matrix, and then we'll do this Kriging to get the actual conditional simulation. And so in this case, we do not need to store anything, and the computational cost become as much as a blob computations. And all we need to do, we need to repeat this process. Now, maybe, I want to kind of expand on this idea a bit and kind of explain how far we can go with this idea. Sometimes, we didn't talk much about the dispersance parameter estimates. And, typically, we need to compute some kind of Remel estimates for those dispersion parameters. And we need to compute maybe the corresponding feature information. And these computations can be done again in a matrix-free way. And these were actually some of the earlier work I did with my collaborator Somak. So we have a paper in GRSSB and one in EJS that explain these kind of computations. And what we actually did, we developed some trust region methods to do these computations. Then comes other kinds of interesting questions. So the computation that I showed you applies for kind of simplest conditional autoregression model, where we only in the conditional distributions depends only on the 4 nearest values. So one of the questions that can come is what happens if we have higher neighborhood order models? So the distributions of the spatial variable at any grid point depends not just 4 neighboring points, but maybe 8 neighboring points or 12 neighboring points or maybe 24 neighboring points, etc. So what would happen if you increase these dependencies and create kind of more complicated model? Now, it turns out that if we have a more complicated model, so we can kind of go back and look into the simplest case. Here we only have like the 4 nearest neighbor, but we are thinking maybe the conditional distributions depends on maybe 8 of these or maybe 12 of these, etc. So then we need to think what would be the corresponding inverse covariance matrix for these kind of models. It turns out that the inverse covariance matrix arise in this A matrix right here, and so we need to replace this W matrix by something else, by the inverse covariance matrix of this more elaborated model. It turns out that for higher neighborhood orders, the inverse covariance matrix can be is nothing but actually a positive polynomial of the matrix W, and this W matrix is the inverse covariance matrix for the 4 neighbor models. And so in the calculations, the only thing that will change is we need to replace W by some positive polynomial of W. But then what will happen is for this new matrix, there would again be a rectangular decompositions, because if we replace this W by P of W, then the spectral decompositions will change, Now the eigenvalues will change, eigenvectors will remain same, but the eigenvectors will will change to some positive polynomial of the eigenvalues of W. And so it's a minimal change. Even though it's a polynomial, it would still be a sparse matrix. So all the computations will remain same. Then there is interest in what we call the fractional Gaussian fields. And so we can think them as intrinsic versions of Maton random fields. So for fractional fields, what happens is we have additional parameters. These are kind of fractional parameters related to the Hertz coefficients or the long range kind of dependence. So in this case, if we look into again a discretization or discretized versions on a fine lattice, fine grid, then the fractional Gaussian fields will have a inverse covariance matrix. It's not going to be W. So there is a typo here, but it's going to be the W power alpha. So where W is the inverse covariance matrix of the four neighbor kind of conditional or intrinsic autoregression models. So the only change that will happen is the change here. We had the previous model, and then instead of having W here, now we need to have W power alpha. But then this does not again change the eigenvalues and eigenvector decomposition. And so we'll again have a rectangular decomposition. So even though this is now a dense matrix, we can do very fast matrix vector multiplications because this the eigenvectors of this W matrix corresponds to the two-dimensional discrete cosine transformation. And so all these steps can be done without storing any of these matrices. And whether it is multiplying because we have everything in explicit form. So everything depends on the matrix vector multiplication. And so whether we are solving a system of linear equations here, a dense system of linear equations, but because of fast matrix vector computations, we can carry out each of these steps. So here the main thing is obviously we have this extra parameter, the fractional parameter alpha. So we need to estimate these parameters, and so the Ramal computations becomes complicated. What we need here is complicated in the sense say we are interested in estimating the dispersion parameters. Now and alpha now is not a convex optimization, and so it becomes a non-convex optimizations, and there is no guarantee that it will convert to the global optima. And so so this is where my earlier work, we looked into the trust region method, and it's a matrix-free computations, but typically, what we found is it converges to kind of two different modes. Often one mode is in the interior of the parameter space, but one local mode we found is on the boundary. And if we go back all the way, so here, I talked about this alpha parameter. So that's the Ramal estimates with with a nugget effect. But the second one, the middle one, is the other local maxima. So so the dispersion parameters or those other parameter computations becomes more challenging in this case. So this takes into account of a very large class of spatial models, not just Gaussian Markov random fields models, but now we can also do calculations for fractional random fields. Now all these calculations I have showed you is for regular grids. So we can have observations maybe at irregular locations, but as long as we can embed everything into a fine regular grid, we can do these computations. There is still interest in maybe irregular lattices. So one question might be, what happens if we want to do this kind of computations truly on a very irregular, large irregular graph, maybe on a road network and things like that. So in this case, what we need to do, we need to think in terms of maybe we have a dependence graph, and then we have some kind of proximity measures. How close, say, node I and node J are. And so typically these proximity measures, and we have a kind of a sparse graph. Then we can also define our conditional / intrinsic autoregressions on this sparse graph. So here the conditional mean will be, I think I have some typos here. This is conditional distribute, mean of the observations at the ith grid point are given all other values. So the conditional mean would be weighted average or of the neighboring values, and the conditional variance would be constant. And so then what we have, we can define our conditional and intrinsic autoregressions again by set of these conditional distributions. And this leads to an inverse covariance matrix W. W is again a sparse matrix, and typically W is proportional to the Laplacian of this weighted graph. Now, in this case, it turns out that the Laplacian of the weighted graph also has a rectangular decomposition. So now we cannot say that the eigenvector corresponds to two-dimensional discrete cosine transformation. There is no such claim, but even so, one can just look into this kind of quadratic form, X transpose WX, and typically this can be decomposed in the following way. With our vertices cross edges incidence matrix, and we can immediately claim that there is actually a sparse rectangular decomposition. And because there is a sparse rectangular decomposition, if we want to do conditional simulations on irregular graphs, then this incidence matrix B actually comes to our rescue. We still have this matrix A as a sparse matrix, so we can solve this sparse system of linear equations very fast. At the same time, we have this decomposition, so we do not need to compute the sparse Cholesky decompositions, but use this kind of rectangular decompositions and then do the conditional simulation. So this is kind of the theory that I wanted to kind of talk about. Obviously, the most challenging case is that we have an irregular graph, and then we are interested in fractional Gaussian field. So it's like we have an irregular kind of Laplacian matrix W, and we are considering kind of fractional power of that. And obviously, that case is not necessarily an easy case, and there are possible solutions there, but it requires some kind of maybe polynomial approximations in matrix form or rational function approximations. Only then one can kind of get faster computations. Otherwise, that's a challenging kind of exercise. So how much time do I have?
You've got 10 minutes in total.
10 minutes in total. So maybe I'll just spend about a couple of minutes and kind of briefly show maybe 3-4 slides on another applications, how we can implement this idea in another application. So here we have this EPA EMAP kind of data from New York, New Jersey, Harvard area. So I'm showing you the map of the region. So all these dots here, these are the sampling locations. So the data are collected on sediments in the New York, New Jersey, Harvard area, and we are only interested in the water body. So the sampling domain is very complex here, and the goal is to study the extent of environmental damage. On each of these locations, some specific data are collected, but I want to kind of explain the spatial modeling part here. So here, obviously, the idea is not to embed these locations on a fine rectangular grid, but the idea should be to maybe embed these locations on some kind of graph, irregular graph, that takes care of the entire water body. Now, obviously, because the sampling domain is complicated, in this case, the Euclidean distances do not make a good sense. So like I picked like 4 points, A, B, C, D. The Euclidean distances are kind of roughly same here, but everything is connected only through water. So if we are, for example, interested in water distance, like the shortest path distance between A and this point here, C, it has to go from A to B and then B to C, and that's essentially twice the distance of like B to C or kind of C to D. Now, the idea is that maybe we embed this region on a fine grid, discard all the points that are on land, and so then we created a fine graph on the water, and then maybe we want to kind of do spatial model on that kind of irregular graph. And so there, if we use this conditional autoregression, or an intrinsic autoregression, they correspond to what we call the resistance distance. And the idea is that distance between A to B, they would be much larger compared to distance between C to D. And again, the idea is simple. On narrow channels, right? The water flows only through the narrow channels. And here on an open sea, water can flow from many different directions. So this distance become much shorter compared to the distance between A to B. Or in other words, there is less resistance here compared to the resistance between A to B. And so there is a natural interpretations of some kind of flow-based model with the conditional and intrinsic autoregressions. So we implemented this kind of model in this context. The data is a bit complicated, so the data is coming from sediment toxicity test. So what they do, they expose some sensitive organism to sediment collected from the toxic site, and they also collect sediment from a reference site or a control site. And so here the sensitive organism is this Amphilixa abdita. It's a shrimp-like amphipod, very sensitive to oil pollutions and other compounds. And so the actual data that comes in kind of 2x2 table form. On every spatial locations, we have a 2x2 table where N amphipods, they are exposed to the case sediment. N amphipods, they are exposed to a control sediment. And we have counts of deaths and counts of survival. And so even though these are like binomial likelihoods, we might be interested in different quantities like log odds ratio, log risk ratio, or log survival probability ratios. And so maybe I would skip some of these some of these stories, but the whole idea is that we can estimate these log odds ratios or log risk ratios or log survival probability ratios, but we want to combine the test results, and that's where we can use our spatial linear mixed effects models. Maybe we have additional covariates, and we have the spatial random effects, and then we can kind of do the prediction. Main thing here is these nugget effects or the residuals, because these are coming from odds ratio, risk ratio, etc. They have they don't have constant variance. So the instead of constant variance like identity times some constant, here we have kind of different variances in different locations. And so our spatial models are slightly more complex. So we have to account for these different to account for this heteroscedasticity, we have a diagonal matrix here. Otherwise, the computations are very similar. And so so we did those computations. Here I'm showing you the block computations on the entire region for 3 different regression models. I'm showing you also the standard error computations. I don't have time to explain, but maybe we can talk later. And we did kind of more, and eventually we have covariates, and then we looked into the prediction map of log odds ratio, log risk ratios, and survival probability ratios in the entire region. So what I did here, we embed them in a very fine graph. So it has maybe about 250,000 nodes, something like that, and each node may have up to 12 neighbors, and so we are dealing with fairly good size matrices, and we are doing all the calculations, and we are able to do that because we are using this kind of fast matrix vector computations, and we are not kind of storing any matrices. So with this, I'm going to stop here.
Okay, thanks very much, Debashis. I think we've got a couple of minutes. Are there any questions we can squeeze in? If you just want to raise your hand. Oh, it seems quite quiet. Maybe people have got to get off on the hour. Yeah, I mean, I'm going to ask the obvious one. What's the software for doing this?
I'm developing a software. I
Mm.
have R functions written. So MATLAB has a lot of very smart matrix functions.
Right.
Including incomplete Cholesky decompositions. They
Yeah.
have this CMLQ for this fast linear solving. Slowly but surely, some of these functions are now coming in R, because R now has several sparse packages. So at some point, I think all the functions will get transported to R. I am developing an R package, but it's going to take some time, maybe another year. Right now,
Okay.
it's just a bit messy,
Yeah. No, I know what that's like, for sure. Okay. So watch this space. Okay. So yeah, we've got like 30 seconds. So I'll just say thanks again for presenting. Really interesting. And yeah, on behalf of everyone else here, I really enjoyed it.
Thank you very much. I mean, Zoom talks are always,
Yeah.
I find it very strange, but yeah.
Yeah, you kind of talk into the void. Well, everyone was listening, I'm sure. Okay. Well, take care. Thanks again.
Thank you, and hope to
Thank
see
you.
you sometime.
Yes, I'll be in touch by email.